Introduction.
I like to drink the juice as it is nutritious. Juice tastes good, especially when it is chilled. Yeah, I agree with you. Please pass the ice cubes to me. I want to put 1 or 2 more into my glass. Sure. Ashish, I want to ask you something. Yeah, sure. Why ice cubes are melting down? When we put the ice cube into the juice, then also it gets dissolved. Why? Okay, I'll tell you. Melting of ice is an example of thermodynamics. Nothing in the universe is cold, you see. Everything in the universe radiates heat to its surrounding. The entropy of universe is continuously increasing. Due to this entropy, ice cubes are melting down. Okay, now I got the answer of my question. It is quite interesting to know about that fact. I want to know more about that. Can you please tell me? Today we will discuss more about the thermodynamics. Objectives. At the end of this lesson, you'll be able to define thermodynamics, explain thermodynamic process, understand mode of transference of energy, describe internal energy, understand pressure-volume work, define enthalpy, differentiate extensive and intensive properties, calculate heat capacity, know about calorimetry, analyze relationship between delta H and delta E, explain laws of thermochemistry, understand bond enthalpies, define spontaneous process, calculate Gibbs energy. Thermodynamics. The branch of science which deals with the quantitative relationship between heat and other forms of energies is known as thermodynamics. Thermodynamics is primarily based upon 3 fundamental generalizations. First law deals with the equivalence of different forms of energies. Second law deals with the direction of chemical change. Third law helps to evaluate the thermodynamics parameters like entropy. Basic terminologies in thermodynamics. System. A system is defined as that part of the universe which is under investigation. For example, if we are studying the effect of temperature on the properties of water, then water will be taken as the system. Surrounding. The part of the universe other than the system is known as surroundings.
For example, if a reaction mixture is taken in a test tube, the reaction mixture constitutes the system. The walls of the test tube constitute the boundary, and everything else is the surroundings.
System may be classified into 3 types. Open system, closed system, isolated system. Open system. A system which can exchange mass as well as energy with the surroundings is called an open system. Closed system. A system which can exchange energy with the surroundings but not mass is called a closed system. Isolated system. A system which can neither exchange mass nor energy with the surroundings is called an isolated system. State of the system. State of the system refers to the conditions of existence of a system when its macroscopic properties have definite values. For example, the state of gaseous system can be defined by its pressure, volume, temperature, and amount. Once these minimum numbers of macroscopic properties are fixed, the other properties automatically acquire definite values. Variation in one or more macroscopic properties brings a change in the state of the system when other macroscopic properties attain new values. The macroscopic properties are thus called state variables. Initial state refers to the starting state of system in equilibrium. After interaction with surroundings, the system attains another equilibrium state, which is referred to as a final state of the system. Thermodynamic process. The operation which brings about the changes in the state of the system is termed as thermodynamic process. A thermodynamic process may be further classified into following categories. Isothermal process. It is a process which is carried out at constant temperature. Adiabatic process. It is a process in which no heat exchange occurs between the system and the surroundings. Isobaric process. It is a process which is carried out at constant pressure. Isochoric process. It is a process which is carried out at constant volume. Mode of transference of energy. The exchange of energy between the system and surroundings can occur in two important modes. Heat. The transference of energy takes place as heat if the system and surroundings are at different temperatures. If the system is at higher temperature, the energy is lost to the surrounding as heat. If the system is at lower temperature than the surroundings, the energy is gained by the system from the surroundings. Heat is represented by Q. Work. The transference of energy may take place in the form of work if the system and surroundings have different pressures. Let us consider a gaseous system which is enclosed in a cylinder fitted with a movable piston. If pressure of the system is higher, the piston will be pushed up until the pressure of the system becomes equal to the pressure of the surroundings. If the system is at lower pressure, piston will be pushed down until the pressure of the system becomes equal to that of surroundings. Internal energy. Internal energy is made up of kinetic and potential energies of the constituent particles. The internal energy is a state function, and the internal energy changes when heat is transferred from system to surroundings or from surroundings to system. The internal energy of an isolated system is constant. The internal energy of a system can be changed into two ways: by allowing heat to flow into the system or out of the system, by work done on the system or by the system. The change in the internal energy is given by delta U equals Q plus W, where Q is the heat supplied to the system, W is the work done on the system. The above relation is the first law of thermodynamics. Pressure volume work. Consider a cylinder containing a gas is fitted with frictionless piston. If the external pressure is slightly lower than the internal pressure, then the piston will move upwards to a length until external pressure becomes equal to the internal pressure. If the volume and cross-section of the cylinder is V and A respectively, then work done by the system is equal to P into A into L, which is equal to P into delta V. Reversible PV work of an ideal gas. Consider an ideal gas be enclosed in a cylinder of volume V, fitted with a frictionless piston, and the external pressure is P. If the difference of pressure is infinitesimally small, then increase in volume is also infinitesimally small. Now, work done by the system due to pressure-volume work is also small. The total amount of work for expansion of an ideal gas from V2 to V1 against a constant external pressure P is given by minus 2.303 nRT log P1 upon P2. Enthalpy. Enthalpy, the state function, is used to measure heat changes at constant pressure. H equals U plus PV, and delta H equals delta U plus P delta V plus V delta P. At constant pressure, delta P equals 0, therefore delta H equals delta U plus P delta V. This equation can be written as delta H equals QP. Delta U and delta H are related by delta H equals delta U plus delta NGRT, where delta Ng refers to the number of moles of gaseous products minus the number of moles of gaseous reactants. Extensive and intensive properties. Extensive properties. Properties of the system which depend upon the quantity of matter contained in it. Examples are mass, volume, energy, heat capacity, enthalpy, entropy, free energy, etc. Intensive properties. Properties of the system which are independent of the quantity of matter contained in it. Examples are pressure, temperature, density, specific heat, viscosity, surface tension, etc. Heat capacity. Heat capacity of a sample of a substance is the quantity of heat needed to rise its temperature by 1 degree Celsius. There are two types of heat capacities: heat capacity at constant volume and heat capacity at constant pressure. Heat capacity is an extensive quantity. For solids, Cp and Cv are equal, and for gas, Cp and Cv are different. Heat capacity is directly proportional to the amount of a substance. Q is equal to product of Cv and delta T, where delta T is equal to Tf minus Ti. The molar heat capacity of a substance is its heat capacity for 1 mole of the substance. The specific heat capacity is the amount of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. Q is equal to C into M into delta T. Both specific heat capacity and molar heat capacities are intensive quantities. Calorimetry. Calorimetry is an experimental technique of measurement of the amount of heat evolved or absorbed in a chemical reaction. The process is carried out in a vessel called calorimeter, which is immersed in a known volume of a liquid. Knowing the heat capacity of the liquid in which calorimeter is immersed and the heat capacity of calorimeter, we can determine the heat evolved in the process by measuring temperature changes. Delta U measurement. Those chemical reactions in which heat absorbed at constant volume are measured in a bomb calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost to the surroundings. A combustible substance is burnt in pure dioxygen supplied in the steel bomb. Heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Since the bomb calorimeter is sealed, its volume does not change. No work is done as the reaction is carried out at constant volume in the bomb calorimeter. Temperature change of the calorimeter produced by the completed reaction is then converted to QV. Delta H measurement. Measurement of heat change at constant pressure can be done in a Measurement of heat change at constant pressure can be done in a calorimeter. We know that delta H is equal to QP. Heat absorbed or evolved at constant pressure is also called the heat of reaction or enthalpy of reaction. In an exothermic reaction, heat is evolved and the system loses heat to the surroundings. Therefore, QP will be negative and delta RH will also be negative. Similarly, in an endothermic reaction, heat is absorbed and system gains heat from the surroundings. Therefore, QP will be positive and delta RH will also be positive. Relationship between delta H and delta E. Enthalpy is the sum of internal energy and PV energy of the system. It is also an extensive property and state function. It is mathematically given by the relation H equals E plus PV. Delta H can be determined experimentally. Delta H is equal to H2 minus H1, which is equal to summation of HP minus summation of HR. For exothermic reaction, delta H is positive. For endothermic reaction, delta H is negative. Delta H represents the heat change taking place during the process occurring at constant temperature and constant pressure. Delta H and delta E of a reaction are related as delta H equals delta E plus delta P delta V. This relation can be written as delta H equals delta E plus delta NGRT, where delta Ng is the change in the number of gas moles. Heat of reaction. It is the enthalpy change taking place during the reaction when the molar quantities of reactants consumed and those of the products formed are in accordance with a balanced chemical equation. Delta H2 minus delta H1 equals T2 minus T1 multiplied by Cp of products minus Cp of reactants. Enthalpy of reaction expressed at the standard state conditions is called standard enthalpy of reaction. Example. Let's take an example on relation between delta H and delta E. The enthalpy change, delta H, for the given reaction is minus 92.38 kilojoule at 298 Kelvin. What is delta E at 298 Kelvin? Let us see the solution. Here the given values are delta H equals minus 92.38 kilojoule. delta Ng is equal to 2 minus 1 plus 3 equals minus 2. R equals 8.314 into 10 raised to the power minus 3 kilojoule per mole per Kelvin. We know that delta H is equal to delta E plus NgRT. Therefore, delta E equals delta H minus delta NgRT. Now we put the values in the equation and calculate. We get the result delta E equals minus 87.42 kilojoule. Hence, the value of delta E is minus 87.42 kilojoule. Various forms of enthalpy of reaction. Enthalpy of formation. It is the heat change taking place when 1 mole of a compound is obtained from its constituent elements. Standard enthalpy of free elements is taken to be 0. Its value gives the idea of chemical stability of the compound. Enthalpy of combustion. It is the heat change taking place when 1 mole of a compound undergoes complete combustion in the atmosphere of oxygen. It is always negative because combustion processes are exothermic. Enthalpy of dissolution. It is the heat change taking place when 1 mole of the substance is dissolved in large excess of solvent so that on further dilution no appreciable heat changes occur. Enthalpy of hydration. It is the heat change occurring when 1 mole of anhydrous substance undergoes complete hydration. Hydration is exothermic process because it involves the bonding between the water molecules and central metal ion. Enthalpy of fusion. It is the heat required to change 1 mole of the solid substance completely into liquid at the melting point. Enthalpy of vaporization. It is the heat required to change 1 mole of the liquid substance completely into vapors at the boiling point. Enthalpy of neutralization. It is the heat change taking place when 1 gram equivalent of an acid is neutralized by 1 gram equivalent of a base in dilute solutions. Enthalpy of hydrogenation. It is the enthalpy change occurring when 1 mole of an unsaturated organic compound is fully hydrogenated. Enthalpy of transition. It is a heat change occurring when 1 mole of the substance undergoes transition from one allotropic form to another. Laws of thermochemistry. Lavoisier-Laplace law. The enthalpy change taking place during the reaction is equal in magnitude but opposite in sign to the enthalpy change occurring in the reverse process. Hess's law. Hess's law states that the enthalpy change taking during the process depends only on the initial and final states and is independent on the path by which the process is carried out. Hess's law helps us to calculate the enthalpies of many of the reactions which are practically not possible, such as enthalpy of formation, enthalpy of transition, enthalpy of hydration, etc. Bond enthalpies. Bond dissociation energy is defined as the energy required to break the particular bond in a gaseous molecule. It is a definite quantity and is expressed in kilojoule per mole. In diatomic molecule, the term bond dissociation energy is same as bond energy, but in polyatomic molecule having more than one similar bond, the term bond dissociation energy is not the same as bond energy. Bond energy is average amount of energy required to break 1 mole of bonds of that type in gaseous molecule. Delta H not of the reaction can be calculated from the knowledge of bond energies of reactants and products. A spontaneous process. The physical or chemical process which occurs in a particular direction under a given set of conditions, either of its own or after proper initiation, is called a spontaneous process. All natural processes are spontaneous processes. A spontaneous process cannot reverse of their own under a given set of conditions. Any process, physical or chemical, occurring in this universe will be spontaneous only if it involves increase in the entropy of the universe. For a process to be spontaneous, delta S universe must be greater than 0. If delta S total is equal to 0, then it implies an equilibrium state. Gibbs energy. The energy freely available from the system at particular set of conditions which can be put into useful work is called Gibbs energy. Out of the total energy associated with system, a part of it is random energy, which is non-convertible into work. The Gibbs energy can be represented as G equals H minus Ts. Gibbs energy is state function, extensive property, and has units joule per mole. Change in Gibbs energy during the process is given by G2 minus G1, which is equal to delta H minus T delta S. Gibbs energy change of the system is related to delta S total by the given relation. Delta G of system is equal to minus T delta S total. Gibbs energy change of the system at particular condition represents the useful work obtainable from the system other than PV work. Standard Gibbs energy of formation. The free energy change taking place during the formation of 1 mole of the compound from its constituting elements at the standard state. Delta GF naught of free elements at their standard state is taken to be 0. Standard free energy change is related to the standard free energies of reactants and products as delta G naught is equal to summation of delta GF naught of products of minus summation of delta GF naught of reactants. Delta G naught is related to delta H naught and delta S naught of reaction as delta G naught equals delta H naught minus T delta S naught. Delta G naught is also related to the equilibrium constant as delta G naught equals minus 2.303 RT log K. Did you know? The word entropy was invented by the German physicist Rudolf Clausius in 1865. Energy cannot be reused once it has turned to heat and dissipated, just as we cannot rebuild an igloo once the snow has melted. Temperature indicates the direction of internal energy flow between bodies and the average molecular kinetic energy in transit between those bodies. Thermal energy is really a form of kinetic energy between particles at the atomic or molecular level. The greater the movement of these particles, the greater the thermal energy. Summary. Let us summarize what we have learned. The branch of science which deals with the quantitative relationship between heat and other forms of energies is known as thermodynamics. A system which can exchange energy with the surroundings but not mass is called a closed system. The transference of energy takes place as heat if the system and surroundings are at different temperatures. The transference of energy may take place in the form of work if the system and surroundings have different pressures. Internal energy is made up of kinetic and potential energies of the constituent particles. The internal energy is a state function. Properties of the system which are independent of the quantity of matter contained in it are known as intensive properties. Heat capacity of a sample of a substance is the quantity of heat needed to raise its temperature by 1 degree Celsius. Calorimetry is an experimental technique of measurement of the amount of heat evolved and absorbed in a chemical reaction. The energy freely available from the system at particular set of conditions which can be put into useful work is called Gibbs energy.